Okay, and I'm now sharing it. Are you able to see the screen?
Yes, sir.
Yes.
Yes, sir.
So in today's experiment, we'll be demonstrating the different nonlinear characteristics of incandescent lamp. So far in our Ohm's law or DC network theorem, it is covered to you now. So there we have assumed that resistance are following the linear relationship, isn't it, between voltage and current. So V is equal to I into R. But in case of incandescent lamp, tungsten and carbon filament incandescent lamps, we'll see that they are not demonstrating linear characteristics. So in that case, how can we check whether what is your steady state current? That will solve, and with that solution, we'll try to cross check whether whatever nonlinear VI characteristics we are getting for these two different filament lamps, whether they are acceptable or not from the experiment. Okay, so main objective of this experiment is first to find out the VI characteristics mostly for the carbon and tungsten filament lamp. Once you get the characteristics, then from the characteristics we'll just find the slope, which will give you, if you plot voltage in the as a independent and I is as a dependent axis, then you will get conductance. If you take the other way around, you will get the resistance. And looking at their value, we can say whether the resistance is constant or it is having a positive temperature coefficient or negative temperature coefficient. Those things we'll try to understand from the VI characteristics, and also we'll do the steady state operation, and we'll see whatever experimentally the value of current or voltage drop across the two sets of lamp which are connected in parallel. So those things we'll try to cross check from the VI characteristics which we obtain by varying the source voltage or input voltage or excitation voltage. So these are your objective. And as we were discussing, carbon filament lamp is not used for the illumination purpose. It is for to put some voltage drop across a circuit where it is required, or maybe for the heating purpose. And we should not use it at a very high temperature because carbon filaments start disintegrating, and that's why the wall of the lamp will get blackened. So that's why it is not recommended to operate at a very high temperature. And in case of carbon filament lamp, those kind of restriction is not there. It is working at fairly high temperature and is filled with inert gas, and fairly well known for its use as a illumination purpose. The tungsten filament lamps. Okay. So this is what our circuit diagram. We have a one auto transformer which will connect with our 230 volt 50 hertz supply. That is our usual household supply, and this is a single phase auto transformer through which using this slider position we can change the voltage level from 0 to 270 at the most, which we'll be using. Its other name is also variac, which we often use. We'll be using two MI kind, it is written, but it is not actually MI. Right, it should be used. We should use MI kind voltmeter because it is moving iron type, because it is AC. And this one is your external resistance which you add, and there will be some drop once the circuit will be closed, and then rest of the voltage out of this 230 few voltage will be dropped here if you connect REXT with the circuit, and then rest of the voltage will be across this parallel combination of these two lamps. Okay. So we'll be using 2 voltmeter and 2 ammeter to find out the branch current or the current drawn by each lamps, and the rheostat, and these are all the equipments, and the lamps are already there. So those. So this step I am not just going through because we'll be playing the video there, you will be able to see. So first step, what we'll do, we'll not connect this REXT, we'll just take this position here. I'll just show. So we'll just take it here, slider position. Then what will happen? REXT won't be there. So then you gradually increase the voltage level from 0 to 20, then 30 or 40 in that step. If you want to go for the final step, you can go 20, 30, 40 at the steps of 10. Or here for this particular experiment, we have taken 20 steps and we have gone from 0 to 220 volt. Okay. And we'll be measuring what is the voltage across this, what is the voltage across the two lamps, and these two will be same when there is no external resistance. So otherwise, because of this drop at REXT, because of the IREXT, V1 plus IREXT will be V1 will be IREXT plus V2. So like that. If REXT is not there, then both are same. And then we have to note down the current through these two lamps, and we should keep on noting those once we keep on increasing. So we should always, when we'll go in the increasing part, we'll go like that, 20, 40, in that way, 80, 100, and then ultimately we'll reach 220. Then from the 220 we'll go on the decreasing side, and then at the steps of 20 we'll come 200, 180, that way. So that time also we keep on recording all the current reading through the tungsten and carbon lamp, and then we'll take the average of it. Why? Because once you keep on increasing, then because of the heating effect, temperature will go high. So accordingly, your resistance may vary. That's why it is done. So this is the first step, and these are the list of the apparatus. Auto transformer range is this, and it should be how much is your VA? I don't remember right now. There will be one more part, which is your volt ampere, kV or VA. Okay, voltmeter, ammeter range. We'll see that ammeter range for the carbon one we should use the milliammeter, because milliampere range, because otherwise it is not difficult for us to read. Other one is 0 to 1 ampere. If we take, it's enough. Okay. So these are the thing which was theoretically given just for your understanding, and accordingly the graphs were plotted. And then uh, we'll just ignore this. And then the next procedure is increase the resistance REXT for the maximum value, and note all the meter reading at the steady state for the maximum auto transformer output voltage, and then enter the reading in the appropriate column of the table 2, and then from the graph we need to estimate it. How it is done, I'll just show once we complete it. So let us now play the video. I don't know why it is not playing. Can you hear?
Sir, we cannot hear the voice.
Now?
No, sir.
No, sir.
Sir, while sharing, there will be option of include system audio. We have to tick on it.
I did that only. I don't know why. What shall I do? I'll leave and then join? Or
Just stop sharing and then start sharing. And there will be option on the left include system audio.
got
Okay, now as our circuit
Is
is
it audible
complete,
now?
now we can start taking the reading.
Yes, sir.
You can see the same.
Yes, sir.
So I'll just play it.
Okay, so in today's class, let us perform the experiment number 7, which is characteristics of carbon and tungsten lamp. So for that, let us first concentrate on the circuit diagram as it is given in your lab manual. You see there are different components. Let us identify them first and then verify that from the circuit, which will be demonstrated right now. So you can see this is the auto transformer or the variac, which will able to provide 0 to 230 volt AC voltage. Okay, so this is the variac part, uh, the corresponding experimental setup. So with this variac, you can increase the voltage from 0 volt to 230 volt. So here we can go at the most 270 as it is seen from the variac dial, but we'll go for this particular experiment till 220. Okay, so this is your main. From here, this is your 230 volt 50 hertz source, which will be going to variac, and from that variac it will go to your circuit. This is the point where the variac is connected. Okay. So next is the rheostat. So you can see from the circuit diagram, from variac it is going towards rheostat, which is a variable resistance. So this is your rheostat, which is shown in the panel. So it is internally connected. So it is having two terminal. You can see from here. Earlier also in the beginning initial classes it was shown there are two terminal. One is here, another is there, and this is connected at the back side of this board, which you can see from the front side like this. So this is the minimum position and that is the maximum position. So you can vary between these two points, right? This, as you can see, this is your tungsten lamp and this is your carbon lamp, right? And we are using total 2 voltmeter. 1 voltmeter is connected as it is shown across the variac. So this is this one, this is your V1, which I have connected across the variac like this. So these are connected in parallel. I have connected this voltmeter parallel to auto transformer or variac, because auto transformer is connected at this point, right? Then the other voltmeter, which is voltmeter 2, this is connected between rheostat and the variac. Uh, between rheostat, this is your V2, one point of the rheostat, other point is the variac. So in between two, I have connected this voltmeter 2. This is your voltmeter 2, which is connected like this. One terminal of the rheostat, other terminal is the terminal of the uh, variac. So this is the two terminal of your variac, right? Then other two are the ammeters. This is the ammeter, ammeter A1, ammeter reading A1, which is connected for the tungsten, right? So I have connected in series with tungsten. You can see that through rheostat, I have connected the ammeter, and then ammeter is going to the tungsten lamp, and from tungsten lamp it is returning to the terminal of the variac to close the circuit, right? In the same way, I have connected another ammeter which is actually taken in the milliammeter range, because through carbon lamp very low current will be flowing, so it will be easier for us to read if we use milliammeter range ammeter. So we are using that. This is our A2 and that is connected in series with your carbon lamp, right? So you can see that from rheostat again we are connecting this ammeter 2. This is our ammeter 2, and then ammeter 2 through carbon lamp, and carbon lamp to as it is returning to the terminal of the variac. Okay, so this is how we are preparing the circuit. Okay, once more I am demonstrating. Starting from the variac, this variac output is there. Then from variac to rheostat, then from rheostat one terminal is going to this voltmeter, which is measuring the drop across the rheostat, and through this we are closing the circuit. We are closing the circuit like this. From rheostat, one path will go to the ammeter A1, and through ammeter A1 to tungsten lamp, and then tungsten lamp to variac. Similarly, other terminal from the rheostat, from there is one another ammeter, which is ammeter 2 for carbon lamp. So from this ammeter we have connected in series with carbon lamp, and from carbon lamp it is closing its circuit at the terminal of the variac. So this is how we complete our circuit. This is all about the circuit connection or preparation of the setup for the experiment. Okay.
Okay, now let us move to the part where we'll take the reading for the VI characteristics by increasing your voltage at the step of 20.
Okay, now as our circuit is complete, now we can start taking the reading. So you can see the same reading table 1 I have prepared in rough for the calculation. So we'll go with first with increasing current from 20, 40, 60, 80 in that way till 220, and then once we reach 220 again we'll come back from there in the decreasing case, so at the steps of 20 volt. So this is what we'll do with the rheostat at the minimum position. So this is the minimum position of the rheostat, and with this we are taking the reading. So now it is in the 0 position, so gradually we are increasing the voltage from here, which will be reflected in this voltmeter V1. So this is your voltmeter V1, and if you verify the voltmeter V1 and V2, you will see almost same reading. Okay, and I have connected the voltmeter between in 300 scale because it is maximum will go to 20, so we cannot go for the 150 volt scale, so we have to read the scale above. Okay, in the dial. So what is the top scale that we have to take? So gradually I am increasing the voltage from 0 to 20, and as it is a nonlinear scale, this is a AC voltmeter, so you cannot see very well, but still this is for 20 here, and then you can check here, this is also for that also we have to take the above scale, and here also it is not very well understood. For the carbon lamp minimum current is flowing through it, and I have connected for the carbon lamp A2 in the milliammeter, so it is 0 to 100 between almost close to 0, so very few uh, I mean the magnitude of the current is very low here. And for the tungsten lamp we can see it is point little more than 0.2, little less than 0.25, so we can record it at 0.25 here for the tungsten lamp, but this will be more clear when we'll tungsten is 0.25, carbon is, let us take point, it is very close to 0, so let us take it as 10 milliampere. This is in milliampere range. Okay, so let us now gradually increase the voltage. So let us go to 40, and again here it is not very well understood what is the difference. From the 60 onwards it will be clearly visible if we keep on increasing. So for 40 also let us take the reading like this. Here it is 40, there also in that V2 voltmeter it is at the same position. So you can see it is near, it is not actually gone to 40 but close to that actually, and we can see the uh, A1 reading which is at zero point 0.3 ampere. So 0.3 for tungsten, and for the carbon again here it is little uh, what we can see between 100 there are 4, so it is approximately 25 we can take. Okay, 25 milliampere. for the carbon. And then let us now go to 60. So now here you can see it is clearly visible in the voltmeter V1. If you uh, just see from the top, almost it is close to 60. It is 60. So for the 60 volt V1, what is your V2? V2 is little less than 60 actually because of the small internal drop. So we can approximately write it as 60, and then we'll take the reading for the tungsten, which is 0.37, and for the carbon it is clearly 50.
Okay, so now let us move to the next part.
So you can see gradually we have populated till 180. Now let us do again for the 200 and 220. So last few increasing steps. So we are reaching 200. So for that the drop across resistor it should be little less than one. It is what should I say? It is 190, 94 kind of 94, 95, approximately 195 approximately. And this is, if you now go through the milliammeter reading, it is 165, which is for carbon 165 milliampere, and for the tungsten it has reached to almost 0.7. Then this is the final one which will reach to 220. So for 220 drop approximately 214. For the carbon lamp it is 175 milliampere, and for the tungsten it is 0.74. So once we are through now the increasing order, let us now reduce it. So from 220 we will now reach to 200, noting at the voltmeter V1. So we have reached 200, and then for that what is the voltage drop across resistor, we'll just verify. It has reached around 194 kind of thing, so we are not noting it. We only now have to note down the reading of the ammeter. So for the tungsten it is little less than 0.7, so let us take 0.69, and for the carbon it is little less than 65, so around 163 we can take it. So it is 163, little less. In that way we keep on reducing. So we'll now go to 180. So for 180 let us take the carbon lamp reading. It is 152 or 153 kind of, so we'll take 153. And for the tungsten it is between 6.65 and 66, so let us take 0.65. So in that way we will now complete this table. We are not demonstrating each and every reading, just like that we have to continue.
Okay. So now only thing left is the steady state readings.
Now let us perform the steady state operation, and with that reading we'll verify what actually we are getting from the VI characteristics which we got from this table. Once we plot it, then only we'll be able to get it. And then will record the steady state value with the maximum voltage, which is 230, as you can see here. This is denoted at V0 in the table 2 for the experiment. So we set it at 230 volt, and then we keep the rheostat in the mid position to have the 50% of the full value, so which will be approximately 100 ohm, because it is a 200 ohm resistor, variable resistor, so max it can reach from 0 to 200 ohm resistance. So when we keep at the 50% position, we get approximately 100 ohm here. Okay, so we'll verify that by recording the drop across the lamps. If you note the reading V2, so this reading is basically what 230 minus drop across the external resistance, then what is applicable over the two lamps which are connected in parallel. So this we can see it is supposed to be 155. Okay, so we have taken this reading which is 155, which is as per the table it will be V10. So this is the drop across your lamps. Then what is the drop across the rheostat? This is your rheostat. So this drop is 230 minus 155. So 230 minus 155, we'll write it here. This is your 230 volt input. 155 is the steady state voltage drop across the lamps, and this I10 and I20 is the steady state current through these two ammeter. So this is the ammeter for the tungsten lamp. So you can see it is 0.61. So we'll record this table parallelly will complete, which is 230. This is 155, and then we record I1 as 0.61, and this I2, which is for the carbon, it is 140 milliampere. So that indicates it is 0.14 ampere. So if we put it there, it is 0.61 plus 0.14. So if you complete this calculation, you will approximately get it as 100 ohm. So we have taken REXT, this is your REXT as 100 ohm, and we got this steady state value. Now let us do it again with the maximum external resistance. We'll set it to 200. This is the maximum resistance, which is 200, and for that we just record the voltmeter reading. So voltmeter reading, if you would see here, this is 230 as usual, because we keep it its maximum value, and then drop across the lamps, it will be how much? It is 105 or 110, between that. So let us take 107 something, and then we record the reading across the this is for carbon filament lamp. So this has come as 110, so 0.11 ampere, and for the tungsten this is little less than point, so let us take 0.49. So this is all in ampere. Ampere. This is volt. So once you get this reading, then you can draw the load characteristics. I'll prepare the table characteristics, and then over that I'll overplot this load characteristics. Then it will be clear. Then only we can complete the other part, which is the estimated value from the graph. So these two will get from the graph, and then we'll be able to cross check whether the BI characteristics, how much valid we got it, okay, from the plot, right? So with this, our experimental reading, everything is completed. Now we have to complete the drawing part, I mean the demonstration part of this table, so that we can get a BI characteristics for the tungsten and carbon lamp. So with this, we conclude the experimental part.
Okay, so once this is over, then this is what we got from the experimental data, which we have tabulated here. So we have gone at the steps of 20 and then we got this reading. A1 is for the tungsten filament lamp, and A2 is for the carbon, and then we take mean of these two, and then once you have the mean, then you can divide with V2 by A1, because V2 is actually giving you the actual voltage across the lamps after the drop at external resistance, but here it is very less. Anyway, we have divided this by this mean, so we got the resistances for the carbon as well as the tungsten filaments. And once you get average A1, average A2, then total current is equal to average A1 plus average A2. So this is your total current which is passing through the voltage. So this is your source. So here is your REXT, and here you have two lamps. This is how your circuit is complete. So this current is your A1 plus A2 is equal to I, total current. Okay. So this will be needing when we'll do the plot. So what we do first to get the VI characteristics, we'll plot along x-axis the voltage, and then along y-axis A1, mean A2, and total current as well. So here you can see that for carbon, this is your current is in milliampere, so it is very low current. So it is on the lower side. Black one or it is dark blue. Okay, so that is your carbon VI characteristics for the carbon filament lamp. Green one is for the tungsten filament lamp, and total current is the blue one. Okay, so now on top of that we should use the load characteristics plot. Okay, so we don't know actually, right? So what is the load? So what is there? This is your source, which is 230.
मैंने उधर वो भी चला दिया था ना, वाटर हीटर दोनों एक साथ.
So this is your REXT.
जब
Is there any question? Okay, so what actually to find out the load characteristics, what we are doing when there is R external resistance, when REXT is equal to 100 ohm, then how can we plot the load characteristics? So we can assume that load is having a negligibly small resistance in one case, so we can short it. So in that case, what we can do, we can just erase this load by a by a short circuit. So it is having almost zero resistance. Then what will be the current through it? What is this I current, IL? When this short circuit, it is V 230 divided by 100 is equal to 2.3 ampere. This is your load current. And what is the voltage? Input voltage? Input voltage is equal to 230 volt only. This is one case. Another case is load may have a very high resistance. So if it is too high, then we can approximate it as an open circuit. So when it is open circuit,
then IL will be 0.
IL will be 0 and VI will be 230. So if you can vary the load resistance between 0 to infinity, and that if you do linearly, if it is changing, then we can get a plot like this. So this is the case where it is 2.3 ammeter, and this is your 230 volt, and this is your 2.3 ammeter 0. So we get two coordinate. One is 230 volt 0, another is what is the, I mean, I am talking about the drop across this. When there is a short circuit, then drop across load is what? R is 0 means IL into 0 is 0. So we got a coordinate like this. And when it is here, then IL equal to 0 means across the load we are getting voltage 230. So we get these 2 points, and if we join these two line, these 2 points, then we will get the load characteristics like this. So for any kind of load in between, any kind of load resistance, here if we can now just draw the plot between voltage and total current, then that will give us the current through the parallel path. So for that, what we are doing, see here, this is black one is your carbon characteristics, and blue green one is your tungsten filament lamp characteristics. So when we add them up, we get the total current through it, which is passing through the circuit, and that where it is intersecting with the load characteristics, that is this. So at this point, at this particular point, what is your voltage? Voltage is approximately, so it is around one, this is 40 and 60, so 155 sort of. I don't know how much is our drop across it. It is 156, yes, isn't it? So this is the case. Estimated 156, here it is 155. So this is the case. So when at this when the drop across two lamps is equal to 156, then what is the branch current? So that we'll get from this black arrow. So you see from this VI characteristics, we are getting the branch current. For the carbon, it is 0.15 ampere. For the tungsten, it is 0.61 ampere. So that we have, sorry, that we have recorded here. Okay, and what we actually got from the experiment, using the ammeter, we got these are the values. So now if you compare, it is almost same. So we can say that our VI characteristics, what we get is following the actual one. Mostly we got the near to the thing. Okay, so there is one. This is one case. Another is when we change our REXT to 200. Then what is your case? What is your load characteristics? The initial point will be this, open circuit part will be this. This one only will change to 200 and it will be 1.15. So I have joined here, and then that 2 point we have joined. So it is intersecting the blue plot, which is total current. It is through this point. So at this point, what is your voltage? Voltage is around 110 or 111. 110 we'll say. And at 110 volt, what is the current for the from the VI characteristics? That is 0.5 for the tungsten and 0.11 for the carbon. And experimentally we got 0.49 and 0.11, so which is very close. So whatever we got from here is acceptable, right? And one more thing, if you just check the plot of this, so this is your V input. V input is equal to I REXT plus VL, drop across load. Okay, so then what is your VI characteristics? So it is VL is equal to plus VI minus I into REXT. Or when we try to express, we just want to plot VL versus IL. So it is VL actually here, and this is your IL. So now if you just check the equation, it is like there is one intercept and there is a negative slope, right? So this is how we get our VI load characteristics, which is having a negative slope. This is one more point to note here from this equation. So we are plotting VL IL plot. Well, VL is your independent and IL is your dependent. So see, we have from the table, I have drawn the graph for you in Excel. You are supposed to do it on your graph paper and just check whether you are getting similar kind of value or not. So almost we can say as we are getting close value, so it is acceptable, experimental, satisfactory. So these are the discussion. What you interpret, I already gave some clue. So based on that, you try to write what happens, how you can interpret the VI characteristics from the point of view of their slopes of the plots. Like slope is equal to conductance or resistance based on the choice of the scale. So whether it is monotonically increasing or decreasing or it is changing. So based on that, you can comment whether it is having a positive temperature coefficient or negative temperature coefficient. Why we increase and decrease the value of lamp voltage and then take the average, that also I discussed. Account for the differences, if any, between the predicted and the observed steady state operation. So when we try to plot, there will be some kind of quantization. So when we take the reading, we cannot take very accurately. So maybe the minor variation we are missing out. So we have to take the approximate one. So accordingly, our things may get changed little bit, but not very drastically off. So if it is too different, then we cannot accept. Okay. So these are the conclusion characteristics of have been exemplified. Nonlinearity has been demonstrated from the plot itself. You can see it is not linear. There is a knee point kind of thing for the carbon. Here it is like this, and the temperature coefficient is found negative, while that for tungsten is found positive. So that you have to check by taking the slope at two different zone, and then that I leave up to you. If this is the point where you can ponder and you can write. Okay. So this I leave for you to write the conclusion and the observation. These are the very important parts. So when you write a report, after the tabulation, this plotting and then writing the comments on the result, what you are obtaining, whatever results you obtain, how you can validate it. That is a very important part of any experiment. So we always, when we check the reports, we focus on this part: discussion, conclusion. So try to write carefully these parts. Okay, so if you have any question, you can ask now. I'll upload meanwhile the videos. Already is it uploaded, or I'm not sure. Anyway, I'll upload again.
It is already uploaded.
Okay, okay.
So it will be uploaded already uploaded under experiment number 7.
Yeah. PPT has been also uploaded.
Class material, I hope you will get it here. So see, all the video recording is there, PPT is also there. Okay. Okay, so if you do not have any question, then we can close it for today. So there was one slot for experiment 7. So in that slot, Bhiman sir will take your he'll demonstrate the other experiment, which is series RLC circuit.
Okay, sir.
Okay. Okay.
Okay, sir.
Okay, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.